plan today is I'm just going to finish off the non-parametric base stuff, and then Ryan's going to take over and talk about convexity and optimization. Any questions about anything before I start? All right. So, to remind you, we were doing problems from the non-parametric Bayesian point of view where we had a function space, we had a prior, we observed data, and you get some sort of posterior on that function space, and we did estimating a CDF, estimating a density function, estimating regression function, and so on. We got a little flavor from how those things are done. Today I just want to finish up talking about things that are non-parametric regression from the Bayesian point of view, showing something interesting that happens, and then we'll be done with this. So consider again a non-parametric regression model. Y is f of x plus epsilon. And we talked about doing this from the point of view of taking f to be a Gaussian process. It's a slightly different way of thinking about it. We can always estimate a regression function, and again, let's think in one dimension for simplicity, by expanding it on an orthonormal basis. So let phi1, phi2, phi3 be your favorite orthonormal basis, like polynomials, orthogonal polynomials, or sines and cosines, whatever, wavelets even. And we can always write f this way. The only unknowns are the thetas. And in fact, it's possible to rewrite the non-parametric regression problem completely in terms of trying to, how do I estimate an infinite sequence of thetas? And I've written that model kind of abstractly at the beginning of page 653. So in statistics, we call this the many normal means model. And the model is like this. Yj is theta j. 1 over root n, epsilon j, where here, it goes from 1 to infinity. You can think of if I did initial estimates of these coefficients, call those the yj's, they would equal the true value plus some noise. And if I had n observations, the standard deviation should be something like 1 over root n. So you can think of this as just being a re-expression of the regression problem. In fact, there's a whole series of papers in statistics which make this very rigorous. You can take density estimation, regression, and many other problems and formally prove that they can be converted into this so-called many normal means problem. And a lot of times people do that because when you want to prove theoretical results, it's often easier to do it in this framework. And then you know that whatever you get here converts back to a density estimation or regression problem. So that's a kind of a commonly used thing in statistics, well, less commonly used in machine learning. But you can just think abstractly too of just starting with this problem. I observe a noisy measurement of theta j, and there's normal noise, between 0, and then there's this 1 over root n, which represents that in some sense this is really coming from n observations. And the fact that the initial object estimating is really some function f, and we're going to assume some smoothness about f, how does that get reflected in these coefficients? And a very natural way to do that is to make a restriction like this. The parameter space is usually taken to be set of all theta, so now this is an infinite vector. But if you took an arbitrary infinite vector, it would be pretty much unestimable. Just like an arbitrary function, you can't really estimate. We need some sort of smoothness assumptions to it. So in the many normal means problem, that's characterized this way, that one assumes something like this. So let's take a look at what this is saying. P is some number here, like let's say 2. And you're saying that theta j squared times j to the 2p summed up must be finite. What does that mean about the theta j's? How could that stay finite? Well, they must be dying off pretty quickly, right? But that's kind of like saying f is smooth, because if this is an expansion and a basis, and if these coefficients die off quickly enough, that would make f smooth. In fact, it can be proved this is precisely a characterization, if you use a certain basis, of what's called a Sokolov space. We dealt with Holder spaces, I think, but there's a similar thing called a Sobolev space, which is nothing other than saying that the p derivative exists. So if I told you it has functions, if I have functions such that this is finite, that's called a second order Sobolev space. That's the same, that's just basically like the kind of spaces we dealt with when we did the bias and variance coupling. That's exactly the same as requiring p equal to 2 here. Say this is finite with p is equal to 2. So p characterizes the smoothness of the space. And this is just a coefficient way of characterizing functions. And the reason why I'm doing this is what I'm about to show you is much easier to show you using this model than using the original regression model. In fact, there's actually a connection between this and the original model. Because if I took as a prior the thetas to be normals, then this function becomes a Gaussian process. This is a random normal function. So, and under a certain regularity condition, the reverse is true. So it's another way of looking at that Gaussian process prior, actually. It's just thinking of it as some expansion, and the coefficients are the things you put a prior on. You put normal priors on them, you get a normal prior on that. That's another way to think about that normal distribution. And so, what I want to tell you, though, is something pretty interesting that people noticed in the early 2000s, which is the natural. So suppose now let's think about it this way. We're really thinking about them as functions, and I want to put priors on them. How would I do this in a Bayesian framework? If I want to estimate theta in a Bayesian framework, how am I going to do it? It's a non-parametric problem because there's infinitely many parameters. The data are normal because I'm assuming here. So the kind of natural conjugate prior would be to take theta j to be, let's say, normal, 0, 1, what do I call it? Tau, this. That would probably be the simplest prior. And it's easy to compute posterior now, because you can actually compute posterior distribution for each theta j separately. It's just a normal code. So now you get the posterior is that theta has a normal distribution. You can see the usual positive. However, now an interesting question arises. These prior variances have to be chosen. And there's two kind of restrictions you'd like to have. One is that you'd like that the prior sits in the space. That is, when you draw randomly from the prior, you get a function in the space. But another question is, if I look at the posterior distribution and ask, at what rate does the posterior converge around the true value? Those are two different questions. So, here's an interesting result, which is, here's what happens. So, if you take tau I squared, call it Q, tau I squared to be, I don't want to confuse okay, there it is. Suppose I write, oops. Doesn't matter if I call it J or I, but suppose I take tau j squared to fall off 1 over j to the 2q. Why polynomial? Well, that's a pretty good guess about how things are going to have to operate. You can try other things, but you'll discover pretty quickly that if things are going to work at all, you're going to probably let them die off in a polynomial way. So the prior variances are getting smaller, smaller, smaller. We need that because we need the thetas to get smaller, smaller if we have any hope of staying in this parameter space. But now it turns out an interesting thing happens. The requirement to make sure you stay in the space is that Q has to be bigger than P plus a half. How do you know that? I actually have the calculation there, and it's just Markov. You can check that if you want to make sure you put positive probability in any ball in this space, Very simple calculation will convince you. You better take Q better than Q plus a half. However, in a Sobolev space, we know, and we'll prove this when we do minimax theory, but you can probably guess what the minimax rate looks like because we've written rates like this many times before. It looks something like this. We haven't made any of that precise yet in this class. We just keep citing these rates. But when we do minimax theory, remember we've seen things like this in regression before, right? That minimax rate can be something like this. So now you can ask a different question, which is what is the Q you use to get the minimax rate? And the answer is we need Q to be precisely equal to Q plus a half. So there's kind of a weird thing going on. If you want to get the, so here, let me draw a picture of what's going on. This is very hard to picture. Suppose, think of this ball as the parameter space, and think of this as the true value. If I take Q a little bit bigger than P plus a half, then the prior puts mass in the space. However, the rate at which the posterior converges is suboptimal. Now, the odd thing is, if I take Q equals to P plus a half, this might seem odd, but I put no prior, there's no prior probability in this ball, and also no posterior probability in the ball. And yet, I'm claiming the Bayes estimator is converging at the optimal rate. How can that happen? How can I possibly get the Bayes estimator to converge at the optimal rate when there's no prior probability there? Well, think about it this way. Think of the posterior as living out here, but when you compute the posterior mean, you're taking the average. The average could be in the center, even if there's no mass there. And that's exactly what's happening. You're getting the posterior mean ends up being very close to the truth. In fact, converges to the truth at the optimal rate. So one way to try to picture, it's very hard to picture infinite dimensional spaces, but one way to picture it is the priors that give you optimal rates. This is a little bit misleading, but the priors that give you optimal rates have all their mass living away from the truth, and the posterior is living out there, but the mean of the posterior converges optimally. If you try to put prior mass here so you get some posterior mass there, which you would presumably like, you will no longer get the minimax rate. It's kind of odd, right? It's a little bit weird, and it's a little bit unexpected. And I think this was a bit of a surprise. And there are ways to fix it, because you might say, well, maybe I shouldn't use this prior. And indeed, there are other priors that will put positive mass in the space and still get a minimax rate, although they're quite a bit more complicated. So you can't use this simple prior anymore. In fact, an example would be to use a prior which is normal up to some finite number k. So instead of letting j equal 1 to infinity, take to be normal from 1 up to k, and do that for each k, and then take a mixture of those priors. So it's kind of a two-level prior. And it can be shown that that actually gets the best of both worlds. It actually converges at the minimax rate, but it doesn't leave this hole in the space. Okay? The message here is just that the behavior of these things is a little bit non-obvious and subtle. And I think a lot of people who are using these tools don't even realize this. So it's not, this is again not a statement about whether you should or should not use these. This is just a statement that if you are going to use them, you should be aware that they have complicated properties. They don't behave like. So now proving this is very, very technical. So I wanted to make you aware of the result. It's not going to go through the proofs in class. And so what we've seen then is consistency is not so bad. With mild conditions on the prior, you do get a consistent posterior. Getting minimax rates, we now see is much more subtle. A question which I believe is still unanswered is whether there's agreement between coverage. So we talked about the fact that the posterior probability of a set being 95% and the frequentist coverage being 95% is not guaranteed. They do tend to be approximately the same, the Bayesian probability and the probability. In low-dimensional, finite-dimensional fixed models with large amounts of data, they do tend to be approximately the same. There are certain counterexamples which we considered last week. In the infinite-dimensional case, it seems to be that they never agree, or rarely agree, although there isn't a lot of work on it. It seems to be largely unknown what happens. If you're interested in the challenging problem to work on, you might want to see what you can prove about the relationship between the Bayesian shear probability and the coverage probabilities in these infinite-dimensional problems. There's a little bit of work on it, but not a great deal, actually. And in fact, I only really know of two papers. There's a paper by Dennis Cox, and I'm going to say 1984, in the Annals of Statistics. And there's a paper by David Friedman, also in the Annals of Statistics, and I'm going to say around 1999. I'm not aware of much else that's available. So if you don't care about the stuff, you can ignore that. But if your curiosity is piqued, I think these are the two references that I'm aware of that do some investigation about this. So it's kind of interesting that there's this gap in our knowledge about this stuff. All right. Good. So that finishes the section on non-parametric Bayesian inference. And before I turn it over to Ryan, I want to see if there's any questions about any of that stuff. Okay. Great. In that case, we're completely switching topics now. And do some convexity.
So I posted these notes, or Larry posted them on my behalf on the course website. Kind of like the non-parametric regression notes. There's probably going to be a lot more in here than we end up covering, but I just did that so that you guys can have a reference in case you wanted to get a little bit more, or learn a little bit more of what was said in lecture. And I left, I don't know, there's a few sections at the end I haven't filled in yet, so we'll have those filled in by the time we get to them. But the basic plan is to start with convexity and just to kind of saturate our knowledge of convexity itself so we get super comfortable with what that is and why it's important and what its role is in kind of an optimization. And then we'll talk a bit about some bit of convex analysis. So this is kind of the mathematical framework that underlies optimization. Then we'll talk about convex optimization. Mention a few algorithms that may be useful, and the key points we're going to hit are the KKT conditions and duality. So those are two very useful things that you might carry forward from these couple of lectures. So it is true that this may seem like when we're talking about it now not very related to, especially to minimax theory, but there actually is a really interesting connection that we'll hopefully get a chance to explore later in the course after we touch on minimax theory, which is that there are analogous results in optimization that are kind of lower bounds in how well we can do, and they're really in many ways analogous to the statistical ideas of minimax theories. So we'll hopefully get to talk about those. I think that's kind of a cool connection. All right, so just a very brief bit of motivation. So optimization problems are kind of ubiquitous in the sense that everything we've written down so far that we've actually talked about, all the density estimation stuff, the non-parametric regression stuff, the Bayesian modeling stuff, those are all at some level optimization problems that we're actually solving. And so why would we care about it beyond the fact that, well, it seems like maybe somebody else has thought about it, somebody else has probably written software. We can, if we're lucky, we can just call that software and get an answer. So why do we care about optimization? Well, I had kind of two answers to that. The first answer is that what ends up being true a large proportion of times is that of the vast number of tools we have, of algorithms we have for solving the optimization problems, it's not always clear which ones are appropriate in which situations, or better said, which ones work best in which situations. And to understand which ones work best for any particular problem, that requires an understanding of kind of their mechanism. So we can't really do it as a black box if we hope to use it to our advantage in practice. And the other reason is, and this is maybe more along the lines of what we're trying to do in this course, is that often an understanding of optimization itself leads to or contributes to kind of a statistical understanding, which I think is a pretty novel perspective that people have started to see in the last maybe 5 or 10 years, when optimization has become more and more prevalent in the stat and ML communities. But actually understanding something from the perspective of optimization can contribute to our statistical understanding of the problem as well. Convexity, that's the other word that's in the title. So why convexity? Well, the simplest answer is that it's because we can actually understand and solve convex problems in a very broad sense. So there is a software package out that's called CDX. It's written in MATLAB. It's actually a pretty remarkable piece of software. I think most people, again, view it as a black box. But it provides a platform for solving pretty much any convex problem, regardless of its form. As long as it can recognize the problem as convex, it can solve that problem for you. Now, it's not going to be super efficient. It actually generally formulates every problem as what we call an SML, a semi-definite program. So it's not going to actually be the most efficient implementation or the most efficient solver for a problem, but it can solve pretty much any convex problem. So that's just proof that we really do understand and can solve convex problems. Non-convex ones are kind of more done on a case-by-case basis. Now that's not entirely true because there are people who can say a lot more about non-convex problems than I could, but I mean my understanding is that it really is more of a case-by-case basis with a few exceptions. All right, so I put down a few references here. Boyd and Vandenberg is a great textbook. It's called Convex Optimization. It really is a great reference. The other really good reference is Rockefeller's book. It's a lot older. It's called Convex Analysis. And so the way I kind of remember the distinction between convex analysis and convex optimization is that I think of it as follows. Convex analysis is really the turf of the mathematician. It's all the math that lies behind what we need for optimization. Convex optimization is really the turf of the engineer. We kind of treat things as tools that we need to perform optimization, but we don't really care as much about the underlying math. So those two perspectives actually are pretty complementary in some sense, and so between those two books, you'll get kind of a complete coverage of the field. So if you need anything, really those are the two books that you can turn to.
And Ryan, that's free, right?
Yeah, yes, thanks for pointing that out. The Boyd and Vandenberg book is free. It's online. It's about, if you just go to Steve Boyd's website or Leith and Vandenberg's website, you can find it on their websites. I think it's about 350 or 400 pages. It's pretty long. The Rockefeller book, on the other hand, is like 120 pages maybe. It's a really thin paperback book. And it's also written in small font. It's from 1970. It's very hard to read, I have to say. It's not something you can pick up and it's not like an armchair read. It's something you really have to be committed to understanding. But it's really terrific. And then a shameless plug is that if this interests you, then you should take our course. It's called Convex Optimization. It's usually taught in the falls. I've been one of the teachers for the last couple of years. I recognize a lot of people from that course who are taking this course. Actually, just for curiosity, how many people have either taken that course, the 725 course, or have taken a course on convexity optimization before? I just know. Okay, so it's not nearly as much as I thought, but that's fine because we're going to just kind of start from the basics. So those of you who have taken that course, I'm sorry, you may find yourself a bit bored, at least at this, as we go through kind of the basic stuff, because it'll be somewhat of a repeat for you. Okay, so this is like level 1 of convexity. really where we start off with, is just convex sets. Okay, and even if you haven't taken the course on this, I'm sure at some point you've seen something like this. If not, you just know what a convex set is. So we're just going to start off, like I said, with the basics. So a set C, it's going to be a subset of Rn. It's called convex. Provided that the following property holds. So if you give me any 2 points, x and y, that are in the set, and you give me also some value of theta that's between 0 and 1, then the point theta x plus 1 minus theta y is also in C. Okay, so this right here, as I move theta from 0 to 1, this just parameterizes the line segments between x and y. Okay, so all this definition is saying is that if I take any 2 points from my set and I join them by a line, that line has to lie entirely within the set C. Right? So, for example, a set like this is convex because if I take any 2 points, I draw a line in between them, x and y, then any point on that line, in other words, any theta between 0 and 1, generates another point, theta x plus 1 minus theta y, that lies in the set C. Okay, this set, on the other hand, if I draw like a bean, for example, some bean-shaped set, that's not convex, right? Because, well, if I look at that line segment, at some point it's going to escape the set. Okay, so for example, if I take theta to be somewhere close to a half, probably, it's not going to line the set. Okay, so very, very fundamental concept. We can actually extend this, this definition just a bit. And so, for one thing we can do is that we can say that actually I can take what I call convex combinations of points that are larger than size 2. So I can take theta 1x plus theta 2, x2 plus theta 3, x3 all the way to theta k, xk, where the thetas are non-negative and add up to 1, then that sum, which I call a convex combination, the sum of theta I xi, must lie in C. That's also another way of characterizing convexity. I can go even farther, and I can say that actually, if I take the integral with respect to some probability distribution over C, then its mean must also lie in C. These are all kind of special cases where I think about the probability distribution as being discrete. But what I just said is that let's suppose that x is a random variable. That's supported on C. Right, then if C is convex, then the mean of x has to lie in C. So this is kind of like the most general, that's the simplest form, but you can get all sorts of other rules out of this general form. That one's just the case where x takes values little x and little y with probabilities theta and 1 minus theta. Okay, so another thing I just mentioned, but I'll write down on the board, is that a convex combination, we're going to say, a convex combination of points say x1 through xk. It's any combination, it's any linear combination of the form theta 1 x1 plus all the way up to theta k xk, where these thetas are non-negative and their sum is 1. And finally, what's a convex hull? These are this is the last of the important definitions for the set case. So a convex hull of, say, a set C is the set of all convex combinations of points in C. So I write that as C-O-N-V, con. That's the operator, the convex hull of C. It's the set of all points that I get from taking convex combinations of elements of C. So it's the set of all theta I, xi, say I equals 1 to k, such that k is bigger than or equal to 1. So I can take any number of combinations of points as long as the number is 1 or more. And these thetas are all non-negative and they sum to 1. Okay, so we have convex sets defined by this property, that one, convex combinations of points, and it's in a convex hull. Yeah?
Does it have to be a finite combination?
It doesn't actually. I can have uncountably many combinations as well. I can have countably many combinations, so an infinite number, but I can also have an uncountable number of combinations. Good question. So convex hulls, you wouldn't be surprised by their name. They have the following property. Convex hulls are convex. So if I take the convex hull of any set, it's a convex set. And it actually is, in some sense, in a precise sense, it's the smallest convex set containing whatever the set is. Okay, so C is just some arbitrary set. Suppose this is C. Its convex hull is the smallest convex set containing C, and we get it by taking the convex combinations of points in C. So in this case, it's actually going to look like this shaded region. We're going to capture all the lines. Yeah.
Is it necessary to have a whatever property to one? By definition, is it possible to set a equal to 2?
You're asking if I get the same thing here if I set k equals 2? Well, certainly if the set is finite or countable, if C is finite or countable, it'll be the same thing. I'm not sure that's going to be the same as. Good question. Yeah, maybe. I'll come back. I'll think about that. So if C is a countable set, if C is countable in points, then certainly I think that's going to be true. I don't know if that's true if C is not countable. Okay, so we're going to be relying on a bunch of notions from basic topology, so point set topology. So if you've forgotten, I'm not going to go through them here because you don't have that much time. But if you've forgotten, I would definitely recommend going back to your notes or some old textbook or Wikipedia and remind yourself what a closed set is, open set, what the interior of a set is, what the boundary of a set is, the closure of a set. All these things hopefully should be familiar to you, and if you're rusty, like I said, just go check those out again. All right, so some examples of convex sets. Just real quick, I'll just pull a few from the notes here. Empty set is convex, right? Because I have to know that something's true for all points in the set. Well, there's no points in the set, so vacuously it holds for all points in the set. Hyperplanes are convex. So this is the set of all x such that, say, A transpose x equals B for a vector A and a real number B. Half spaces are convex. So this is the same thing as this definition, except for I relax it to inequality. Okay, so half space is like the dividing the n-dimensional space in two via this normal vector A. A very basic example is a norm ball. So if I have a norm, then it's always true that a norm ball is convex, so it's the set of all x for which the norm of x is less than or equal to t. This is any norm on Rn, so it could be like one of the LP norms. It could be, it really just could be any norm. And so you can check that all these are convex just right from the definition. Okay, so just take that first definition, just take any 2 points, take their convex combination, prove that it's still in the set. These sets are all convex. Okay, and now we just kind of take all we do is we're going to intersect in half space a finite number of times. And we're going to get polyhedra. Polyhedra are actually simple to define, but deceptively complicated. They're very, very complicated objects. There's a whole theory of convex polyhedra. There are whole books written about convex polyhedra. Actually, in some ways, it's a pretty beautiful subject, but they can get very complicated. All we're doing is we're just intersecting half spaces. So I'm going to take the finite intersection of, say, m half spaces. The set of all x for which a I n equals x is less than or equal to bi for all I between 1 and n. And I'm going to write this kind of a bit of an abusive notation, but it's much more convenient as just a set of all x for which ax is less than or equal to b, where that b is just, I just take these b's and I stack them on the components of a vector, and this a is just the matrix where I put on its rows these AIs. And I interpret this inequality component-wise. So that means that every element of AX is less than or equal to every element of B component-wise. So if I compare the components, I just get these inequalities back. Okay, so polyhedra are convex. Again, just right from the definition, we can see that. I wrote down a few more things for examples. You can look at them if you'd like in the notes. I suggest that you at least go through everything I wrote down in the notes. If not, if you're curious, check out some of the textbooks that I wrote down. And here's another one that's kind of a bit outside of this this trend. Is let's look at the set of all symmetric PSD matrices. That's actually a convex set also. Okay, but we're going to have to just define a bit of background before we get to those. So first, I'm just going to define a set of symmetric matrices. I won't do PSD. I'll just look at a set of symmetric matrices. So I'll write that as Sn, and it's the set of all matrices X that are n by n matrices that are symmetric. And we're going to think of this as a vector space. Of dimension n times n plus 1 over 2. So I think people often get confused when we move from vector spaces to matrices, especially in convexity. We'll jump all the time between saying something for vectors and for matrices. People get confused because they think that we need to redefine everything for matrices. Like, what does convexity mean? Not on Euclidean space, but on the set of matrices. Well, don't worry about that. Just think about this matrix as, I'm just thinking about it as an n times n plus 1 over 2 vector space. Because if it's a symmetric matrix, all I have to care about is say it's upper triangular part. And there's just n times n plus 1 over 2 entries there. The fact that they're arranged into a triangle is really not that important. It still is a vector space. I can just think about unraveling it into something vector and then treating it as a vector space. Of course, the operations on the vector space respect that triangular structure, but it still kind of fits our our basic setup. Okay, so that's how I'm going to think about symmetric matrices, an n times n plus 1 over 2 vector space. And now, if I look at the set of PST matrices, so this is positive semi-definite matrices, hopefully no one's surprised by that word, positive semi-definite matrices. We're going to write that as, it's going to be written as Sn plus, and it's the set of all matrices X that are symmetric with n by n, and I have the property that they're positive semi-definite. So we're going to write that like this. It's just kind of like a curly bigger than equal to sign. So that means that, for example, all eigenvalues of this matrix X are non-negative. Or in other words, it means that if I take any vector A, and I do A transpose XA, that's non-negative. That's what it means to be positive semi-definite. So this is also a convex set. As a subset of the space of symmetric n matrices, this is also convex. Okay, that one, why don't we prove that one just so you're not perplexed about why that is. It's very straightforward. We're just going to take two PSD matrices, take a convex combination, check that it's PSD. That's all we have to do, right? Takes two PSD matrices, take theta that's in 0, 1. And let's look at theta x plus 1 minus theta y. So how do we prove that this is positive semi-definite? Well, let's just take the inner product of this with A on both sides. This vector A. And I just get theta A transpose A XA plus 1 minus theta A transpose YA. Each of these guys are positive, right? So the whole thing's positive, so that means this matrix is definitely positive semi-definite. So this has. Okay, actually I didn't need theta to be in 0, 1 here. As long as theta was positive, if I just took theta 1x plus theta 2y, as long as theta 1 and theta 2 were both positive, I would have had the same answer, right? All I need to know is that these two factors here, theta and 1 minus theta, are positive. So that makes this actually a convex cone. A convex cone is something that's convex and a cone, meaning that I can take there's positive combinations of elements and they stay in the set. So you often hear this as referred to as the PST cone, positive semi-definite cone. Okay, I wrote down some key properties there of convex sets. They're, I'll just name them: the separating hyperplane theorem, the supporting hyperplane theorem, and the closed half-space representation of convex sets. We're not going to use any of them, so I'm not going to cover them, but they're actually very important. You'll see that a lot of the things that we end up proving for convex functions can be proved from convex sets, and they rely on those properties. So convex sets are really like ground zero for everything that we do. Is there a question?
Beyond vectors and matrices, are there other objects that are whose convexity is useful in machine learning? Are there more structured objects whose convexity we can talk of? Like usually it is limited to Rn or matrices, which is fine, but are there other objects that are mathematically interesting?
You're saying outside of Euclidean space?
Yeah.
Yeah, that's a good question. Yeah, there are. There actually is. There's a researcher, a visiting researcher here. His name is Subrit Straw. I'd say he's one of the world's leading experts on this exact topic. So he has a bunch of papers. He's actually teaching a class right now called Advanced.
I'm taking that class.
I'm taking that class. Okay, you can ask him that question. He will hopefully be a much better answer than I think. Yeah.
The reason we restrict ourselves to symmetric matrices, like the way I see, instead of positive simplified matrices, form a convex code even.
Yeah, that's a good question. Actually, things end up being a lot cleaner when you restrict yourself to
So that's the
symmetric.
only reason I said.
Yeah, so when we talk about, I don't know if we'll do it, but, I mean, you'll certainly have the tools to do it, but when we talk about subgradients, for example, and just taking gradients of convex functions, you'll see that it's actually a lot cleaner if we work in this n times n plus 1 over 2-dimensional space. And the answer is actually end up being different, by the way. So if you ask about a gradient in one space versus the other, they're actually a little bit different. Okay, so those three properties, like I said, usually you go through them like in detail in a convex analysis course, but we're not going to use them, so I'm not going to talk about them. Just know that they are essential to proving things for convex functions that we'll just kind of write down and assume. And if you took the class actually last semester and you're finding yourself bored in these next couple of lectures, the challenge would be to use the supporting hyperplane theorem to prove the existence of subgradients. So we're going to talk about subgradients at the end of today or tomorrow when we get to them. You can actually prove they exist from the supporting hyperplane theorem. So that can be a challenge if you're finding this too slow. Okay, here's one of the things that I would actually attribute to Boyd and Vandenberg of that the textbook Common Optimization that they do so well. And I haven't really seen this elsewhere. Is that they really push very, very hard for this notion of operations that preserve convexity. And so they give a really long list of operations that preserve convexity, both for convex sets and convex functions. And I think it's extremely useful to know. I think this and the section on operations that preserve convexity for functions are really the two arguably most useful things to remember from basic convexity theory. And why is this a useful thing to know? Well, it's because actually it actually gets really tiresome to prove that things are convex from the definition. So all these things we could have done from the definition, but we're going to look at some pretty complicated objects, mostly convex functions. And it's not obvious to prove from the definitions that they're convex, or at least it takes kind of some time, and it's pretty tedious. But if we remember kind of a basic set of convex sets, or convex functions, and so here's our basic convex sets: hyperplanes, half spaces, norm balls, polyhedra, symmetric matrices, etc. And we know that there are operations that we can do to them that will preserve convexity. So after we transform them in some way, they'll still be convex. Then we can get all sorts of much more kind of rich convex sets. And if we encounter something in the future, instead of going to the definition, we can say, oh, look, this is just actually a bunch of operations on some very simple convex sets that I already know. And so it's convex automatically. I don't need to worry about that. And so here are a bunch of operations that preserve convexity. I'm sure that I'll miss some because we don't have all the time in the world. So you can always check the Boyd and Vandenberg textbook. Intersection is the first one. So if I intersect any two convex sets, they're still convex. And this is actually true with any number of convex sets, even an uncountable number of convex sets. Okay, it's still convex. And so here I'm just going to actually say in words the closed half space representation because it relates to this. If I have a closed convex set, then I can write it as the intersection of all half spaces that contain it. It's a pretty interesting fact. So that's an uncountable number of half spaces for most convex sets. That intersection ends up being kind of an active intersection of an uncountable number of half spaces. So for example, there's a convex set. Right now you can see I'm going to need an uncountable number of half spaces to actually get that intersection, because I'm going to have to get one for every point along that curved surface. Okay. Oh, actually, yeah, this leads to another interesting way to prove that Sn plus is convex. I'm going to skip that, but just check that out if you're interested. You can prove that the symmetric of positive semi-definite matrices is convex from this property. And when you see this for the first time, it may, to use Larry's nomenclature, it may blow your mind. It is kind of amazing to see that, that it's convex from this perspective. You can take a look. It's just like a couple lines in the notes. Okay, what are some of the other properties? So if I take the affine, if I take an affine image of any convex set, so if I transform it being an affine map or an affine primage, then the set is still convex if it was convex originally. So affine just means linear plus an offset. That's all we're using it to mean. So if I have a function that's affine, I just mean that it's just ax plus b, where a is a matrix and b is a vector. And if I have a convex set, so if C is convex, then f of C, which is the set of all x such that f of x is set of all f of x such that x is in C is convex. And so is the preimage. So this doesn't mean that f is invertible, by the way. I don't mean that at all. I actually just mean the following set. We call it sometimes the preimage or the inverse image under a function f. It's just a definition for any function. It's the set of all x such that, I'll use a different set here than C. I'll say if C is convex and if D is convex. Just to emphasize that these are different sets. They're going to lie in different dimensions generically, right? Because f might map from like Rn to Rm. So the preimage of a set D under F is a set of all x for which f of x is in that set D. So it's also convex. And this one is nice. Now we can start to see how powerful these operations that preserve convexity are. We're going to actually just use this to show that the solution set of what we call linear matrix inequality is convex. So I'm going to look at the set of all points x that are in Rk that satisfy what we call a linear matrix inequality. It's just like the linear inequality, but it's for matrices. So I'm going to take x1 from the matrix A1. So this is just the first component of x, it's a real number, plus x2 times the matrix A2, plus all the way up through xk, ak. And then look at that being matrix less than or equal to b. So what I mean by this is that b minus this matrix, that's a matrix, right? It's a linear combination of matrices, is positive semi-definite. That's what that matrix less than or equal to. Okay, when I rearrange that, I just get b minus this guy is positive semi-definite. Just note the analogy to, you know, the real value analog. I get x1 a1 plus x2 a2. I'm talking about little a's less than or equal to b. That's just like ax transpose x is less than or equal to b. This is the matrix version of that. So we call this a linear matrix inequality. This is actually always a convex set. Regardless of the a's and the b's, of this matrix B and these matrices A.
Yeah. For the second statement, whole B convex implies, I think was B, don't you need some assumption on the rank of A?
No.
If I just take just take 2 points which are certainly not convex, they map them onto, say, I just map them onto one axis, and they turn out to be equal to the axis. Say, for instance, my point is...
yeah, so the domain of this function, though, is all of Rn or something. Its domain is not. I'm not quite sure what you're asking.
Right, so say, for instance, I take my set is 2, 5 and say 4, 5. That's in x, y coordinates.
Okay.
So 2, 5 and 4, 5. And f of x equals ax plus b is just the is just the y coordinate. So 2, 5 and 4, 5 they don't form a convex set, but their projection forms a convex set.
Yeah, so you're asking for the converse statement.
Right, it's the second one, yes.
No, but see, I think you're actually talking about the converse. You're saying that if this is convex, does that imply that D is convex? Well, we're just saying that if D is convex, then this set's convex. Certainly, you gave us an example of where D was non-convex, but the pre-image ended up being convex. It's a good question. All right, so this being convex, we can see directly from the fact that affine preimages are convex, preserved convexity. No checking whatsoever of convexity needed from the definition. So all we do, let's put it over here. All we do is we take, we look at the set S and plus, the set of all positive semi-definite matrices, and I'm going to look at the function f of x, which is going to be b minus x1, a1 plus x2, a2 plus xk, ak for fixed b's and a's. That's an affine function in the x's. K goes from Rk to, again, a space of matrices, but I'm just going to think of that as a vector space. It's an affine function in the x's. It gives me an affine function in the x's. And this guy right here, which we'll call S, or I guess we'll call it something else since I already have S. Call this set D. Then if I take the pre-image of Sm plus under this affine map, I get exactly that set. So it's convex, because it's the affine pre-image of the set of positive semi-definite matrices, which I know is convex. Okay? Okay, I'm going to skip over perspective images and the pre-image images and linear fractional functions, but it does have some relationship to probability. You can show that if you know that a set of probabilities or a set of discrete probability distributions is convex, then using those types of transformations allow you to say that a conditional distribution of probabilities is also convex, so it's kind of interesting. But we just have too much to cover. But it's in the notes. And I'll just mention, I guess, that some very special cases of these affine maps are scaling and affine transformation, or scaling and shifting. So if I have a set that's convex, I can always take alpha times c, and it'll be convex, and I can always take c plus b, say, and it'll always be convex. Those are just two very special cases of affine maps. Okay, so scaling and translation preserved convexity.
Probability example only works for discrete probability.
Sorry, the question
You
was.
said that the conditional probability is complex as well if the likelihood was convex. So does it only hold for discrete probabilities or?
Well, I wouldn't even know what that means outside of the discrete case, because the way that we talk about the discrete case is that if it's a discrete distribution, say with n states, then we talk about we talk about n-dimensional vector space. So if it was continuous, it would be something else. Probably something that Sarit can answer for. Yeah, I don't know, at least not with our tools right now, how we talk about that. Any questions on convex sets before we move on to convex functions? Pretty basic objects, but it's important important to understand them thoroughly. All right, functions, convex functions. So I would claim that convex functions are actually even more important than convex sets because they end up using them kind of way more than convex sets, to be truthful. But it's kind of funny to say that because the two are very closely related, and everything that we know from convex functions can be proven from convex sets. There's a link that we'll talk about called the epigraph. Once we understand that, it's true that everything that we know about convex functions can be proven from what we know about convex sets. But convex functions are just a little closer to the surface for us in terms of what's useful. So a function that goes from, say, Rn to R with domain alright as dom f. This is kind of an annoying thing that you have to do with convex functions. I'll probably get sloppy and start dropping this at some point. But it is kind of important to talk about the domain of functions because not all functions are defined on all of Rn. So for example, log is only defined on for the positive reals. So its domain would be the positive reals. And other functions that we'll talk about don't have a domain, it's all Rn. Like I said, I'll probably get sloppy and I'll stop talking about domains, but at least for now, just think about that as being the values of Rn over which the function actually is defined in some subset of Rn. And we call this function convex provided that the following property holds. So if I take f of theta x plus 1 minus theta y, then this has to be less than or equal to theta f of x plus 1 minus theta f of y. And this has to be true for any x and y that are in the domain. And any theta between 0 and 1. That's the definition of convexity. Again, I would be surprised if you've never seen that before, at least in some context, but there it is in case you've forgotten or never saw it before. It just means that, intuitively, if I draw the graph of the function and I draw the points x and y, the evaluations f of x and f of y, and I join on that graph the evaluations f of x and f of y by a line, that the function has to lie below the line. So quick picture, I draw the graph of the function. Here's x and here's y, and f of x and f of y, and I join it by a line. It's the line segment. Then if I look at f of the point theta x plus 1 minus theta y, so let's evaluate it somewhere in here, then the value of the function is less than or equal to the analogous value on that line segment. Okay, strictly convex is an important extension of this. So a function is strictly convex. This happens if f of theta x plus 1 minus theta y is strictly less than theta f of x plus 1 minus theta f of y. And this, we only require this to hold for theta, I guess I'm right over here, for theta between 0 and 1 strictly. Otherwise, that wouldn't be possible. So just replace that inequality by strict inequality. And this means that the function is actually not flat anywhere. So it's convexity means that it's kind of curved upwards in some sense. Strictly convex means that it's both curved upwards and it's never flat. Okay, so for example, an affine function, this guy, this is definitely convex, but it's not strictly convex. Right? Affine actually get equality there, definitely not get inequality. And concave is just concave or strictly concave. These just mean that, so if f is concave or it's strictly concave, that's just the same thing as saying that minus f is convex or strictly convex. Okay. So actually, affine functions are both convex and concave. And the only functions that are both convex and concave are affine functions. So these guys right here. And the last important definition, and this one sometimes tends to get left out, but it ends up being very important. When we talk about convergence rates for algorithms, which we'll either do now or later when we talk about the minimax rate analogy, I'm not sure when. But strongly convex is the last notion that we need to know. Okay, so we've been going up. Convex, strictly convex means more than convexity, actually means it's sufficiently curved. Strongly convex is even stronger, so hence the name, it's kind of the strongest form of convexity. It's even stronger than strictly convex. And we say that a function is m strongly convex. So this is a parameter. So it's strong convexity is associated with a particular parameter m for some m greater than 0. This means that the function f of x minus m over 2 times the norm of x squared is convex. Okay, so it means not only is f convex, but after I subtract off a quadratic function from it, it still is convex. So I think about it like it's at least as convex as a quadratic. So it's at least as curved as a quadratic function. So that's the strongest. It implies strict convexity, which implies convexity.
If f is twice differentiable, would those two be equivalent to concave and strong?
No, they're not actually.
Convex and strong.
It's a good question. I mean, I can just say the answer right here. So they're not the same. They're very close. But if f is twice differentiable, then strict convexity happens when the Hessian of f is positive everywhere. This means the Hessian of f has to be logarithmed by m.
So it should be uniform.
Yeah. So it's a lower bound for it. So what's an example of a strictly convex function that's not strongly convex? 1 over x. 1 over x, yeah, sure. Right, so its domain is going to be the positive real. So open 0 to infinity. But it's strictly convex, but not strongly convex. Because it's sufficiently curved, but there's no quadratic I can kind of lay down globally that's going to lower bound that function. Okay. Some examples. Again, I'm going to just kind of pick and choose here. I guess we'll stick with norms since we talked about norms for convex sets. So norms are always convex. It's nice because, you know, in machine learning and stats, we often use norms as regularizers. And so the fact that they're convex, we're going to see shortly, is a big aid for computation. It means we can use the solve and solve fast. But a norm is always convex. So if I have f of x equals the norm of x, that's always a convex function. Okay, and so some important kind of sub-examples are the LP norms. P is bigger than 1. And we end up defining the infinity norm. I guess I should maybe say, strictly speaking, I'll look at 1 maybe equal to p less than equal to infinity. And when p is infinity, the infinity norm we define as the maximum of the absolute values of the coordinates of x. So these guys are all convex functions. Okay, how do you see this? Just go straight from the definition. It basically just follows from the triangle inequality and positive homogeneity of these norms. So it's very straightforward, just right from this definition. What if I take p less than 1? It's not convex, yeah. So when p is less than 1, these functions are not convex. And actually, I don't know if we talked about norm balls. So yeah, the norm balls for p less than 1 are not convex. But that's not really a contradiction because those aren't even norms. That's just an abuse of nomenclature. Those are actually pseudo-norms, not even norms. Okay, so when people talk about the L0 norm, it's not really a norm, it's just what we're calling it. Or the L1/2 norm or something, or the LP norm for p less than 1. We just decided to call it that because at one point probably we were lazy, but they're not norms. So any norm is convex, and these are norms. When the LP norms are p bigger than or equal to 1, or p is equal to infinity. And so now we'll jump like we did in the set case to matrices. So I'm going to jump right to matrices, norms on matrices. So I'll think about f of x. So this is a function that lives in the space of matrices. Well, at this point, they don't have to be symmetric or square. We'll say they're n by m matrices. And I can define two matrix norms. So I'm going to do that here. So the first is going to be the operator norm, also called the spectral norm. And we're going to write that as little op. And that's just the sum of the singular values of x. That's completely false, I'm sorry. This is a trace norm. It's the largest singular value of x. Okay, so if I order them like, sigma 1 to be the biggest one, then the operator norm is just the largest singular value. And the trace norm, people also call the nuclear norm or the nuclear norm if you're from Texas. That's just the sum of the singular value. Okay, so these guys are all complex. Okay, quadratic functions, maybe we'll just do quadratic functions, and then maybe let's do two more examples, and then we're almost at the end, so maybe we'll get some more examples. So quadratic function Yeah, QSD, PSD, right. It's kind of misleading because, well, actually, no, it's not misleading. I was going to say in one dimension it's misleading, but it's not. It just means it would be pointed down if it wasn't PSD. So it's convex divided up. The quadratic form Q is PSD, and it's actually strictly convex. In fact, I'll just go ahead and say strongly convex if Q is strictly positive. Because then it is lower bounded by a quadratic, namely itself. Right? We'll see very easily how to prove that once we talk about the equivalent conditions for convexity in terms of derivatives in Hessian in a second, or I guess next time. Okay, that means that least squares, for example, is always convex. This criterion, AX minus B, always convex because it's a quadratic, and the quadratic form is A transpose A, which is always PSD. Okay, and then other stuff here, like that minus 2 B transpose AX plus B transpose B, but that doesn't matter. The important part is just that that's PSD, so least squares is always convex. Okay. A few more. Indicator functions are convex, provided the original set is convex. So I'm defining this to be 0 if x is in the point C, and it's infinity if it's not. It's called the indicator function of C. It's convex if C is convex. I'm just going to define two more, and then after we define these, I think we'll have a really good base understanding of convexity, and then with these functions, plus the operations that preserve convexity, to be able to prove that almost any function that you encounter is convex, provided it actually is convex. Okay, so this is a pretty good list of examples. And we're going through. So the max function is convex. That's one. How do we prove that? Well, you could just actually go straight from the definition of this one also. That would work. And this one is not obvious. This is a function that when you look at it, kind of like, it takes you a second to digest. So we take the log of the sum of exponentials. So we're going to call this thing log sum x because there's not a better name for that, and that's what everyone else does. That's convex. Not obvious that it's convex, right? Because you have a log on the outside, which is concave. But the whole function is convex. And this one's really useful after we see the observations that preserve convexity. Because actually, this can be viewed as an approximation to this, a smooth approximation to this. So the way I remember it is that so suppose x1 was biggest, then e to the x1 is going to be bigger than a lot of the other guys, e to the x2, e to the xn. And that difference would be quite large because we're exponentiating. So when I take the log, I'm basically just taking the log of e to the x1, so I get that x1, which is the max. Yeah. As I make p larger and larger.
Yeah.
Yeah, that's a good point. Yeah, it is similar to the p norms as I make it larger and larger. except for this one has a little bit tighter bounds for how it approximates max. So I guess I can write them down. Oh, the other advantage is this is actually differentiable everywhere. The key norms will be differentiable for key variable 1. Yes, I guess they're really the same in that regard. But this one has a nice approximation factor, which is that if I take the max, it's always less than or equal to the log of the sum of the exponentials. And on the other side, I get max plus log n. So I'm taking the max of a lot of stuff. Log n grows pretty slowly, right? So it means that it's a pretty good approximation. Okay, so that's it. This one. Oh, so I guess on Monday we're going to go through the operations of observed convexity and then we'll learn separating.
Is there